Okay, sorry about the gap. I have to record every 15 minutes, it seems. So, picking up where we left off, this molecule will be likely excreted through the renal pathway, through the fecal pathway, and so we will expect it to go into the small intestines, to the large intestines. In the large intestines, there are plenty of microflora, bacteria in the gut in order to have this azobenzoreductase to reduce this azobenzo group into the sulfanilamide molecule in this amine benzo group. It is actually this molecule here that is the antibacterial. So this is a way of targeting the reactivity and the potency of this molecule and minimizing the toxicity of the overall drug taken by having it be a prodrug only metabolized by bacteria to have its antibacterial effect. So that's actually a pretty smart way for chemists to design a drug that functions only on certain biochemistry in bacteria in order to target this bacterial antibacterial effect. So I just wanted to mention that azobenzoreductase because sometimes we are focusing a little bit heavily on the innate molecules that are endogenous molecules that are inside of biology, that they're inside of our system that are undergoing these biotransformation reactions. But we all know that there are loads of microbes that are living inside of us that also contribute to our overall biochemistry. Okay, so we've covered aldoketoreductase, reductase, and now we're going to look at the metabolism of alcohols, which I'm sure is of profound interest to a lot of college students. So we're looking at ethanol first here, probably the most commonly ingested alcohol. A fairly simple molecule, 2 carbons, an alcohol group, and it actually goes through biotransformation by 2 specific enzymes in the body that are part of an enzymatic pathway for digestion. Now, predominantly these enzymes, alcohol dehydrogenase and aldehyde dehydrogenase, are found in the liver, and metabolism of alcohols is predominantly in the liver. What is interesting about alcohol dehydrogenase in particular, sometimes abbreviated ADH, alcohol dehydrogenase, is that there are actually 2 types of alcohol dehydrogenase. There's type 1 and type 2. Type 1 is found in the gut, and that alcohol dehydrogenase has a certain expression factor in the gut. The second type is found in the liver. And so there's actually 2 different ones. And one of the interesting bits of information that I learned when researching this was that these 2 types fluctuate in expression levels throughout the lifetimes and by sex. So women tend to express low levels overall of alcohol dehydrogenase, both type 1 and type 2, with respect to their age. So when they're younger, they have low levels of expression. When they get into about their mid-50s, women's level of alcohol dehydrogenase expression actually goes up quite a bit. The opposite is true for men. So for men, their alcohol dehydrogenase expression peaks from age 20 to age 30 and decreases for the rest of their lifetime. So their efficiency of digesting alcohols is actually at its peak in their 20s and 30s. For women, it's in their 50s and 60s when they have their peak of alcohol dehydrogenase. It's also postulated that the variance in type 1 and type 2 expression in the gut and in the liver accounts for some people's issues around drinking alcohol, being more susceptible to things like beer, low alcohol content beverages like beer and wine versus liquor. So liquor has a high alcohol content, which means that its absorption, the alcohol transference to the bloodstream is much more quick. And so that means that it's a low volume, high alcohol content transferred to the bloodstream. It's going to be mainly digested in the liver. And if you are a person who has type 2 expression that is higher for some reason, then liquor is going to be an easier beverage for you to imbibe without having an intoxicating effect. Versus if your level of type 2 is low, then liquor is very dangerous for you to drink because you become intoxicated much more quickly. In reverse, some people have a higher level of type 1 expression, which means that they would be able to drink beer or wine and have less of an effect on their intoxication than they would liquor. And the inverse is true there as well. Type 1 low expression in some people means that they cannot drink beer and wine and would actually be more intoxicated than if they were to drink liquor. And so this is really one of the problems with saying, well, I've only had 1 or 2 or 3 drinks. And even if you do that by type, it really doesn't account for the fact that your level of expression and your level of digestion and your level of your age really can shape and change your level of intoxication. So this is why it's a bit tricky to predict people's ability to be sober or not intoxicated based on the number of drinks that they have. Okay, so if we look at this transformation, we see again that this is a facilitated transformation, this time by NAD+. So NAD+ is going to be a very similar molecule to NADPH, except for we're missing the phosphate portion of the molecule. Okay, so now we're looking at NAD+. NAD+ is facilitated as a cofactor in both of these enzymes. The first transformation that happens from ethanol is to form acetaldehyde. So here we've taken the double bonded O and we've oxidized it. The single bonded alcohol group and made it a double bonded O and oxidized it to the aldehyde. And then the second step is to add an alcohol here, so it's an oxidation step where we're going to take and form acetic acid. Okay, so let's look at this alcohol dehydrogenase and its activity. So you notice that we have the NAD+ down here. The NAD+ is our cofactor, NAD+. So that means we know we're going to have a double bonded nitrogen down here. If we add aromaticity to the ring, we know that there will be 1 hydrogen at the top there for our NAD+ species. We also can see that we're going to have this zinc ion that is coordinated here by 2 cysteines and a histidine held in place. So this is, again, a zinc ion that's helping to facilitate this reactivity. And what we're going to do is we're going to draw in our alcohol group here to the enzyme. So I'm just going to use an R group for now to represent any generic alcohol. And we're going to coordinate that oxygen of the alcohol to the zinc center. Okay? And what that's going to do is it's going to draw electron density up and make the pKa of this hydrogen go down. It's more easily lost now, and so we can actually, we can easily now transfer that hydrogen to the sulfur group here and form this intermediate that's going to be the protonated sulfur group. We're going to replace the sulfur group now with the oxygen to coordinate with the zinc center. Draw in all of our double bonds for our NAD+ cofactor. And so now what is capable here is that this negative charge that's now held on this oxygen can fall back into this bond. We can actually transfer one of these hydrogens down into the NAD+. That causes the electrons to move in the NAD+, and what we result in is the formation of, the zinc species. Here we now have 2 hydrogens bound to the NAD+. We form the quinolloid. We have the NAD+ is now NADH as our product. And our alcohol has now been effectively converted from ROH to ROH, a double bonded O. So we now have an aldehyde that's been formed by the alcohol dehydrogenase. So you can already see that we formed our first substrate. Ethanol converts into the acetaldehyde, the aldehyde form, and then we'll use our second enzyme, aldehyde dehydrogenase, to convert. Okay, so here we're facilitating the transfer of of reduction. So usually when you see dehydrogenase, right? So here we're going from an alcohol to an aldehyde, right? And so if we look at this molecule, that alcohol portion has now been taken from ROH to R double bonded O, right? So we're effectively oxidizing this species. So it's the opposite of reduction, right? And so we can think about that back in our system. So here we have NAD plus going to NADH as our cofactor. So this is effectively adding a hydrogen or being reduced. So our oxidation reduction pair is the alcohol and the NAD plus. Where we have reduction happening with the NAD plus, we have oxidation happening at the alcohol center. So that's what's facilitating the conversion here in this reaction. We take the alcohol, coordinate it to the zinc, transfer a proton by lowering the pKa of that alcohol. Now that becomes an oxoanion that can fall back in, lose a hydrogen, add that to the NAD plus, resonate down the electrons, and form an aldehyde as our product.